Hello everyone, welcome to my video on the derivative of inverse trig functions. So before we get to the derivatives, let's take a look at the definition of an inverse trig function. So the first one that we have here is arcsine. So y equals arcsine of x, or sine inverse of x. And this is equivalent to saying, essentially, if you bring the arcsine or the sine inverse over on the other side, the exponent becomes positive, so we get sine of y equals x. What you're doing essentially is you're taking sine on both sides of the equation, leaving us with sine of y, and the sine of inverse, they cancel each other, leaving us with just x. So you have to remember these definitions. This holds true for arccos, arctan, cosecant inverse, secant inverse, and also cotangent inverse. So you have to have all these definitions memorized. One warning is to understand the difference between the reciprocal of the function and the inverse of the function. So arcsine can be written as arcsine of x. So we can write arcsine. I think this is the better notation to use instead of to the -1. I don't want you to get confused with, especially when you have to use chain rule to know not to think of this as an exponent. This is just notation. So arcsine of x is equal to sine inverse of x. Okay, and that's not equal to, so be very careful here. This is not equal to, we'll do it in red, 1 over sine of x. It's not a reciprocal. Okay, this is notation. This means arcsine, not the reciprocal of the function, so keep that in mind. Okay, so now we start with the derivative of arcsine of x. So if f of x equals arcsine of x, then what's its derivative? Let's go ahead and do it together. We'll prove it. So proof, think of f of x equals arcsine of x as y equals arcsine. Okay, and then by definition we just saw that we could rewrite this, or this is equivalent to saying sine of y is equal to x. So this is what we're going to use. And we're going to take the derivative of this implicitly. Notice that we have a y and an x, and we're going to have to apply implicit differentiation. So for implicit, we're taking the derivative on both sides of the equation with respect to x. I'm using the Leibniz notation. So let's start off with the right hand side because it's easier. We're deriving x with respect to x. So we don't have to worry about chain rule. So the derivative of x, we're essentially just using power rule, giving us 1. Okay, so the right hand side of the equation we get 1. Now we're taking the derivative of sine. We know the derivative of sine, but be careful, it's sine of y, and we're deriving with respect to x. So since the variables do not match, we have to apply chain rule. So the derivative of sine is cos. We leave the inside as is, which is y, and then we multiply by the derivative on the inside. We're applying chain rule. So the derivative of the inside is y prime. Okay. So now implicit differentiation tells us to isolate y prime. Go find y prime. So in order to do that, we're going to divide by cos of y. Y prime equals 1 over cos of y. Okay. The issue with this is that we have to express this in terms of x. Y is a function in terms of x. We have a y in here. How do we get rid of the y? Well, what's cos of y equal to? So you have to know a property here. The property is sine squared of y plus cos squared of y equals 1. We've seen this property, you have to know it. And what we're going to do is isolate for cos of y, because that's what we want. So isolating for cos of y, we're going to bring the sine squared of y over on the right hand side of the equation. So this is side work that we're doing, giving us cos squared of y equals 1 minus sine squared of y. Okay. But we want cos of y, not cos squared. So what we're going to do, square root. So square rooting both sides, we get cos of y equals square root of 1 minus sine squared. Okay. So we could substitute cos of y with square root of 1 minus sine squared y. Okay. Cos of y seems a lot nicer, so why are we doing this? We're going to see this in just a moment. So we get 1 over square root of 1 minus sine squared of y. The reason why we did this is because we actually know what sine of y is equal to, because we want to rewrite this in terms of x. Well, we have a relationship between x and sine of y right up here. So it's very customary to come back to the initial equation and substitute when you're doing implicit differentiation, and also we'll see this idea with logarithmic differentiation. So we're going to come in and replace the sine of y with x, giving us 1 over square root of 1 minus x squared. And we're done. So the derivative of arcsine in terms of x is 1 over square root of 1 minus x squared. And that's our answer. So now let's look at the derivative of arccos. So if f of x is equal to arccos, then what's the derivative? Proof. Same concept. We let y equal arccos, or cos inverse of x. And we know by definition that this is equivalent to cos of y equal to x. So let's go ahead and derive this implicitly. Again, you could always pause the video, try this on your own, see if your answers match mine. So the derivative of cos of y equals x. We're going to take the derivative with respect to x. Cos of y. Once more, the derivative of the right hand side is fine. The derivative of x with respect to x is 1. The derivative of cos y with respect to x is, well, the derivative of cos is negative sine of whatever's in the bracket. In this case, it's a y, times the derivative of what's in the bracket. So times the derivative of y. So we'll just leave it as y prime. Okay. Now we solve for y prime by dividing by negative sine of y. Giving us this. But once again, we have to express this in terms of x, not of y. So what we do is apply the same property as we saw before, namely sine squared of y plus cos squared of y is equal to 1. Using this property here, we isolate for sine of y by subtracting over the cos squared. So sine squared of y equals 1 minus cos squared of y. And lastly, we take the square root of the sine. Sorry, of both sides of the equation, leaving us with sine. Okay, so now we could substitute sine of y with the square root of 1 minus cos squared, giving us negative square root of 1 minus cos squared of y. And just like before, we want to express this in terms of x. We know the relationship between x and y is the fact that cos of y is equal to x. So we're going to substitute cos of y with x, leaving us with 1 over negative square root of 1 minus x squared. And this is our derivative. Okay. So f prime of x, negative 1 over square root 1 minus x squared. So now we're looking for the derivative of arctan of x. So we know by definition that we're going to substitute the f of x with y, and we know by definition arctan of x can be rewritten as tan of y equals x. Okay, so essentially we're bringing the tan inverse over onto the other side, giving us a positive exponent. Tan of y is equal to x, and now we could derive implicitly. So let's go ahead and take the derivative of both sides of the equation with respect to x. Again, the right hand side, simple, it's equal to 1. The left hand side, we have to apply chain rule because we're deriving with respect to x, and we have a y here. So it's the derivative of tan is secant squared of y times the derivative of what's inside, which is y prime. Okay. So we isolate for y prime, giving us y prime equals 1 over secant squared of y. And again, we have to express this in terms of x, not in y. So we're going to use a property. The property we have to apply here, it's the fact that secant squared of y is equal to 1 plus tan squared of y. So we could directly substitute this into here. So instead of writing secant squared of y, that's the same as 1 plus tan squared of y, giving us 1 over 1 plus tan squared of y. And now with this substitution, we can use the fact that tan of y is simply equal to x, giving us 1 over 1 plus x squared. And that's the derivative of arctan. So the derivative of arctan of x, written in terms of x, is 1 over 1 plus x squared. Okay, so this has to be memorized. So now we're doing the same thing with arcsecant. So let's go ahead and rewrite it as y equals arcsecant of x, and by definition this is the same as secant y equals x. Let's take the derivative implicitly. So we're going to take the derivative with respect to x on both sides of the equation. So the derivative of x with respect to x is 1. The left hand side, the derivative of secant is secant tan. So secant y times tan y. And since we're deriving with respect to x and we have a y, by chain rule we're multiplying by y prime. Okay, so y prime is equal to 1 over secant y times tan y. Okay, so secant y is okay. We have no issues here because we have the relationship that secant y is just equal to x. So this piece here is equal to x. What we have to do is figure out how to substitute or replace the tan solely in terms of x, not in terms of y. So to do that, we have to apply this property here once more, and we're going to isolate for tan. So we're going to start off by bringing the 1 over, so we're going to get secant squared y minus 1 equals tan squared. And lastly, to isolate for y, for tan of y, we're going to square root both sides. So we get square root of secant squared y minus 1, and that's equal to tan of y. So over here we could express it as y prime equals 1 over secant y, we're going to substitute it right away with x, and tan of y, we're going to substitute it with the square root of secant squared y minus 1. And we know secant squared of y, or secant of y, is equal to x, so this is just going to be x squared, leaving us with 1 over x square root of x squared minus 1. And that's our derivative for secant, 1 over x square root x squared minus 1. So now let's go ahead and prove what the derivative of cosecant inverse is equal to. So first of all, the property, let's mention this here. We know that secant squared is equal to 1 plus tan squared. So the same property applies for cosecant squared. It's equal to 1 plus cotangent squared. Okay, so once you know the secant squared equals 1 plus tan squared, you could just use that to obtain this equation here, this property. So by definition, we have y equals cosecant inverse of x. This is equivalent to cosecant of y equal to x. And again, we derive implicitly. So we take the derivative with respect to x of cosecant y, and that's equal to the derivative with respect to x of x, leaving us with the derivative of cosecant with respect to x is negative cosecant, y times cotangent y, and then using chain rule times y prime, and the derivative of x is 1. Dividing by negative cosecant cotangent y, we get y prime equals 1 over negative cosecant y times cotangent y. Okay, so cosecant y is not an issue. We know we could substitute that using x, but the cotangent, we have to apply this property. So let's go ahead and solve for cotangent. We're going to subtract this equation here by 1 on both sides, leaving us with cot squared of y. And now we're going to square root both sides of the equation, leaving us with cosecant squared of y minus 1 equals cot. This is all underneath the square root, equals cot of y. So we're going to substitute cot of y with the square root of cosecant squared of y minus 1, giving us 1 over negative cosecant y square root cosecant squared of y minus 1. And now we're going to substitute all the cosecants of y with x, leaving us with 1 over negative x square root of x squared minus 1. Okay, and that's our derivative. So negative 1 over x square root x squared minus 1. So lastly, we're going to take the derivative of arc of cotangent of x. We begin by replacing f of x with y, cotangent, arccotangent of x, showing that this is equivalent to, by definition, cot of y of x. Now we're going to take the derivative implicitly with respect to x, giving us cot y equals d dx. So all the proofs here are very similar. And now we're going to derive cotangent. So the derivative of cotangent, remember the rule, if the derivative of tangent is secant squared, the derivative of cotangent, because it starts with a c, is negative. Derivative of tangent is secant squared, so it's cosecant squared times y prime over x. Okay. Yeah, that's correct. And now we solve for y prime by dividing by negative cosecant squared. And now we have to substitute the cosecant squared of y, because again, we want to express this solely in terms of x. So since we know the relationship that cot of y is equal to x, this isn't sufficient for us. So let's go ahead and use our property again and solve for cosecant squared of y. In order to do that, one way of doing it is just to simply multiplying both sides of these equations by negative 1, because we want negative cosecant squared, not cosecant squared. So multiplying both sides by negative 1 gives us negative cosecant squared y equals negative 1 minus cot squared of y. And we could substitute it here. So negative cosecant squared is negative 1 minus cot squared of y. Using the property now that cot of y is equal to x, substituting it into here, we get 1 over negative 1 minus x squared. Okay. On top of it, they're both negative, so we could factor out a negative 1, leaving us with negative 1 over 1 minus x squared. Sorry, x plus squared. X plus x squared. Okay, and that's our derivative. So the derivative is negative 1 over 1 plus x squared. So let me give you a tip and a trick to help you remember the derivatives of inverse trig functions. So we've seen the trick for just the derivative of regular trig functions, and the same thing applies for inverse trig. So notice that if they start with a c, arccos, arccotangent, or arccosecant, if you're taking the derivative, you're going to have a negative that emerges. Okay. And once you know the derivative of arcsine, which is 1 over square root of 1 minus x squared, well, you know the derivative of arccos, because it's the exact same thing, f prime of x, but just with a negative in front. So it's negative 1 over square root of 1 minus x squared. Okay, so that once you know arcsine, you'll have arccos memorized, because we know the fact that it starts with a c is going to make this negative. Okay, arctan, we know the derivative is 1 over 1 plus x squared. That has to be memorized. But once you know the derivative of arctan, you know the derivative of arccotangent, because it starts with a c, so it's going to be the exact same thing as tan, but negative. So negative 1 over 1 plus x squared. And then lastly, for secant, if the derivative of arcsecant is 1 over x times the square root of x squared minus 1, well, we know the derivative of arccosecant, because it's the exact same thing but with a negative in front. So hopefully that's a little trick that helps you memorize your derivatives. So let's take a look at our example here. We're asked to find the derivative given that the function is equal to arcsine of 5x. So first thing you have to catch is the fact that there's a 5 here, so it's not the regular derivative. We have to apply chain rule. Okay, so it's a composition of functions. We have the arcsine function, and then we have the function y equals 5x. So applying chain rule, we're going to start off with the outermost function. So we're going to take the derivative of arcsine. We know that the derivative of arcsine, it's not a cos, it's a sine, so it's going to be positive. It doesn't start with c. So it's going to be 1 over the square root of 1 minus x squared. But instead of x, it's whatever's in its bracket squared, so 5x squared. And then multiplied by the derivative of the inside. The derivative of 5x is just 5, giving us 5 over the square root of 1 minus 25x squared. And that's the derivative. So in this second example over here, we're asked to find the derivative of the square root of x times arccos of x. It's an x. So I urge you to pause the video, try this on your own, see if you can get the same answer as me. So the thing that you have to catch here is that we have a multiplication. This is a multiplication of two functions. So we have to apply product rule. F times g prime is equal to f prime times g plus g prime times f. Okay, so this is the rule that we're going to apply. This is our first function, this is our second function. Let's go ahead and take its derivative. Actually, before taking its derivative, my advice, whenever you have a square root, switch it to an exponent. So I'm going to write it as x to the 1/2 times arccos of x. Okay, you don't have to do this, just this is my advice. So we're going to take the derivative of x to the 1/2 using power rule. So we drop the 1/2, x, subtract 1/2 by 1, giving us negative 1/2. Multiplying by arccos, we don't touch it, we just leave it. Arccos of x. It's separated by an addition because it's product rule, so plus. We're going to leave the square root of x now, so x to the 1/2, and multiply by the derivative of arccos. The derivative of arccos we saw, it starts with a c, so I know it's going to be negative, and it's similar to the arcsin, so 1 over square root of 1 minus x squared. Okay, so let's go ahead and simplify this. This is equal to arccos of x over 2 square root of x. So the x here has a negative exponent, let's get rid of it. We drop it down here, and we have arccos on the top. If your teachers they don't want to see square roots on the bottom, you're going to have to rationalize, so multiply the top and the bottom by square root of x. Minus, here we have x to the 1/2, which we could also write as square root of x divided by square root of 1 minus x squared. Okay, so this is fine, but since you're dividing two terms that have a square root in it, we could put them all under the same root. So your answer could be expressed in this fashion. So in this example here, we're asked to find the derivative of f of x equals arctan of x squared minus 4 divided by x squared plus 4. So I'll give you an opportunity to pause the video, try this on your own. What you have to catch is the fact that we're dealing with a chain rule because we have a composition of functions. We're dealing with arctan, and within the arctan we have x squared minus 4 divided by x squared plus 4. But on top of it, we're dealing with quotient rule because we have a division. So just to remind ourselves, quotient rule, f divided by g, all that prime is the derivative of the top times the bottom minus the derivative of the bottom times the top over the bottom squared. So let's go ahead and do that. Let's start off with taking the derivative of arctan. So f prime of x. The derivative of arctan is 1 over 1 plus x squared. Or think of it as 1 over 1 plus whatever's in its bracket squared. So we could rewrite this as 1 plus x squared minus 4 divided by x squared plus 4, all that squared. Fix this bracket. So that piece is done. We dealt with the arctan. Now we have to deal with the inside. So the inside, what we're going to do is use quotient rule. So we're going to take the derivative of the top. So the derivative of x squared minus 4 is 2x, because the derivative of x squared is 2x, the derivative of negative 4 is 0, times the bottom, we just leave it as is, x squared plus 4, subtraction sign because it's quotient rule, so we have a minus, derivative of the bottom again is 2x, and we multiply by the top as is, so x squared minus 4. All this divided by the bottom squared, so the bottom squared is x squared plus 4, all that squared. Okay, so what we could do next is we could factor out the 2x on the numerator here, and at the same time on the left hand side what I'm going to do is distribute the 2 to the numerator and the denominator. Okay, so we could rewrite this as 1 plus x squared minus 4 squared, the squared's on the outside of the bracket, divided by x squared plus 4, all that squared. This is just properties of laws of exponents, so we're allowed to do this. And over here on the numerator, we're going to factor out the 2x, leaving us with, let me open another set of square brackets, leaving us with x squared plus 4. So this first term over here, we factored out the 2x, leaving us with x squared plus 4. And the second term, it's separated by a subtraction sign. And we're factoring out the 2x, leaving us with x squared minus 4. I'm going to keep that in brackets. Square brackets, all that divided by x squared plus 4, all that squared. Okay. So focusing just on the denominator, this is a bit weird. You don't have to do it this way. There's other ways of doing this, but what we could do is essentially multiply the whole denominator here by this denominator here. Think of it as over 1. So if I multiply this by this and this, what we get on the denominator is x squared plus 4 all that squared times 1, which is just x squared plus 4 squared. So I multiplied this by the first term, by 1. Then there's the plus. And now what I'm going to do is multiply this x squared plus 4 squared times the second piece. But notice there's an x squared plus 4 squared on the bottom. So this x squared plus 4 is going to cancel with this x squared plus 4, leaving us with just the numerator. Leaving us with just x squared minus 4, all that squared on the top. Okay, so we just essentially distributed this by this and this. Okay, next what we have is the numerator. So the numerator we factor out a 2x, so I'm going to leave that here. And at the same time, what I'm going to do is distribute the negative sign. Because we have a binomial afterwards, make sure to distribute, don't forget. So if I remove the brackets, negative 1 times x squared is negative x squared, but then negative 1 times negative 4 becomes plus 4. Okay, so that's a common mistake that students make. Just be careful with binomials. When you have a negative in front, you distribute to both terms. Think of it as a negative 1. And now x squared and minus x squared cancel. Same number, opposite sign. And then we have plus 4, giving us plus 8. So on the numerator we have 8. And then we had a 2 in the front, so we'll just 8 times 2, multiply them together, giving us 16x. And this is the answer. So if you got this, great work. If not, we'll keep practicing. So in this example over here, they're asking us to find the second derivative given the function y equals arccotangent of 4x. So pause the video, try this on your own. Let's go ahead and do this. Let's start off by finding the first derivative. So dy dx. Derivative of arccot is, well, we know the derivative of arctan is 1 over 1 plus x squared. So this is arccot, starts with a c, giving us negative 1 over 1 plus x squared, but it's not x, it's whatever's in the bracket because we have chain rule. So 4x squared. Now to finish the chain rule, we have to take the derivative of what's on the inside. So the derivative of 4x gives us just 4. Simplifying this, we get negative 4 on top over 1 plus 16x squared. Okay. This is the first derivative. Let's go ahead and take the second derivative. So we're going to take the derivative once more. So the second derivative gives us 2 d2y over dx squared. We have a fraction, so you can use quotient rule, but what I would do is I would rewrite this as 1 plus 16x squared to negative 1. Okay. So this is quotient. If you want to use quotient, that's fine. I want to use chain rule. So what I took is the denominator, I brought it up and put it all to the exponent negative 1. So what that does is I'm going to focus on the outermost function. So firstly, we have a constant multiple in the front, the negative 4. So I'm just going to put him right away. And now I'm going to deal with this piece over here. So the derivative of 1 plus 16x squared to the negative 1, well, we're going to start off with the outermost function, which is the exponent, so negative 1. We're going to drop it and subtract it by 1. We're applying the power rule. So dropping the exponent negative 1, then recopying what's in the bracket, 1 plus 16x squared, and then subtracting the exponent by 1, giving us negative 2. So we dealt with the exponent, we still have to deal with the inside. So we're going to multiply by the derivative on the inside. So the derivative of 1 plus 16x squared is 32x. So the 1 is gone, the derivative of a constant 1 is 0, and the derivative of 16x squared is 16 times 2. And because you drop the 2 from the exponent of the x, and you subtract the exponent by 1, giving us times 32. Okay. We could simplify this and write it as 4 times 32. So 2 times 4 is 8, 4 times 3 is 12, giving us 128. So two negatives make it a positive. 4 times 32 is 128. So we get 128x on the numerator. And on the denominator we have, because we're going to drop it, it has a negative exponent, giving us 1 plus 16x squared, all that squared. And this is the answer. Okay, let's make sure our answer is equivalent to quotient rule. So let's do method 2 and do the quotient rule method. So d2y dx squared. Applying quotient rule, remember it's f over g, all that prime, equals derivative of the top times the bottom minus derivative of the bottom times the top over the bottom squared. So the derivative of the top, we're over here now. We're looking at this because we have a fraction. The derivative of the top of -4, it's a constant, giving us 0, times the bottom, which is times 1 plus 16x squared, minus the derivative of the bottom. So the derivative of the bottom is 2 times 16, so 32x, times the top, times -4, over the bottom squared. The bottom squared is 1 plus 16x squared, all that squared. So 0 times this whole term is gone. And then we have a negative and a negative, so it becomes positive. 32 times 4, we saw it earlier, I erased it, was 128x over the bottom squared, which we'll just leave. And notice that both answers here are equivalent. So it doesn't matter which way you do it, it's up to you. Use the method of your choice.